Alright, welcome to Math 330, Section 2, Chapter 1, Population Models. So this is about how to use the knowledge of differential equations that we've already learned so far and apply it to an application, in this case a population model predictions. Let's get started. So far we've talked about this type of population model, and where we've got our differential equation is equal to k times some population. Now this produces an exponential growth model, and this works great if you have unlimited resources. But most of the time you don't have unlimited resources, so there's other models we're going to discuss. So how do we get this population model? Well, first we need to know the number of births per unit population per time. We need to know the number of deaths per population per time. And to actually get the total number of births that happen, we have to multiply our beta times the actual population at that time times the change in time at which those births occurred. To actually get the same number of deaths, we have to multiply our delta by the actual population at that time times the change in time over which the deaths occur. And to get our change in population, we have to take our births, subtract our deaths, and that should actually get us our change in population. To do that, we get this equation. So if I divide by my delta t, I get a differential equation where I get my birth rates per population per time times the population minus our death rates per population per time times our population. You can factor out a p, and you get this differential equation. Well, the big question in this is, what is our beta and what is our delta? So to do this, that depends on the population you're looking at. Now, beta can be a function of the present population times some constant a, or it could be this function where c and d are constants. A is a constant also. The death rate could actually be a constant death rate, or it could be proportional to the present population. It depends on the situation that you occur. Again, h is just some constant which is happening. Alright, so a popular population model is this equation. It's called the logistic equation, and it's used mostly if you have some limiting factors in the population that you're dealing with. K is a positive constant, and M is also a constant, and it's referred to as the carrying capacity of the population, or what is the so-called quintessential population level that the population can sustain over time, and that's what's called M. This population will show up if there's a limited environmental situation, which means limited resources. At some time, the resources start being used up, so the population becomes limited, or a competition situation. If you've had some biology classes, you've heard of the predator-prey model. So where you have some predator species eating the prey, and you can model the prey population or the predator population using this logistic equation. And the other one is what is referred to as a joint proportion situation, and that usually is associated with the spread of some disease. You have a certain amount of your population who's already been exposed to the disease. How will it get spread over time, predicting how much time it will take for everybody in the population to have the disease, or 80% of the population having the disease. And the last one is if is what's called the doomsday or extinction population model. So that requires a little tweak to the logistic equation. So if you see up here, it's m minus p. Here we have p minus m, and that basically says at what population, if you go below this m value, which now is called the threshold population, if you go below that, you have a really good chance of the population that you're modeling going extinct or just disappearing. So those are some ways the population models are used. So let's practice solving some population models. So here is a population model. This is problem 5 on page 82 of your book, and they want us to predict a solution to this in 2 ways. They want a direction field with multiple solution curves, and so you can see we have multiple solution curves here. Here is the initial condition at t equals 0, 8, and you can see how it starts at 8 and comes down to this number line right here. There's like an asymptote right here about occurring at 5. I wonder why it occurred at 5. I wonder if you can think about why it should occur at 5. And then here I have it starting at 4, and you can see the population increases to 5. And then here I have it starting at 1, the population increases to 5. And then here it's 0 for a while and then jumps up. I believe I give an initial condition somewhere in this range, and you can see how it goes to 5. And then I give an initial condition that was below 0. So there's another asymptote down here where it's at 0. And I wonder if you can tell me why it would have an asymptote at 0 at that point. And I give it an initial condition below 0, which is kind of not possible with population, because populations are usually always larger than 0. But mathematically, you could have a negative population, so I just wanted to show you how it goes away from 0 if you start with a negative population. And if you're in between 0 and 5, it always goes to 5, and if you're above 5, it always goes back to a population of 5. Alright, so how do we actually solve this and actually get a prediction for what x of t is? Well, this is a separable differential equation, so we can separate and integrate both sides. The right-hand side is quite easy. We can do that. The left-hand side is a little bit more difficult. We're going to have to do integration using partial fractions. So if I go through all the rigmarole with that, the equation that pops out that needs to be valid is this one. And I'll let you guys do all the algebra to verify that this is correct. So from this, I get 2 equations. I get 1 equals a 5 times a, so a has to equal 1/5. And the other one I get is minus a plus b has to equal 0, so a has to equal b. And so a and b are equal. So if I convert my integral up here using partial fractions, I get this integrals down here, and now I can solve. Alright, so we have this integral to do, and we've done a lot of these lately, so that's basically a logarithm integral that comes out. We can factor out the 1/5 of both integrals. I can multiply by 5 throughout the whole expression, use properties of logarithms, take the exponential on both sides, and now I need to solve for x. I also simplified the expression on the right-hand side by using properties of exponents, and I create a new constant called x0, x of 0 right here, and then we need to solve for x, and in doing so I have to do some algebra, I have to do some more algebra, and even some more algebra, and finally I get this solution. So now I have to find x0, my integration constant, and so I apply the initial condition, And now I have to solve for x0, and then we go through all the math for solving for x0, and we find out that x0 has to equal a negative 8 divided by 3. I apologize for the way these equations look, but for some reason my software is trying to argue with me. And if I put them back in, this is my solution for x. Alright, so let's look at this population problem. It's problem 21 on page 83. It says, suppose that the population for a country satisfies the following differential equation, where k is a constant. If the population in 1960 was 100 million and was then growing at a rate of 1 million per year, predict the country's population in 2020. So we know we have this differential equation, and I believe they're measuring all the population in terms of millions, so that 200 in there should be really 200 million, but we'll just assume our population numbers are all written in millions. Our initial condition is 1960, and we have 100 million people. I'm going to claim t equals 0 at 1960. And then I'm going to try to predict what k is, because k is an unknown. How am I going to do that? Well, I need to figure out what the derivative of the population is. And I can do that because the problem states the derivative, or how the population is changing right here at a rate of 1 million per year. So my change in population is 1 million for every 1 year, and that should equal k times my population. Well, that rate is happening in 1960, and the population is 100 million, so I plug that in there. Now I can solve for k, and I get a k of 10 to the minus 4. Now I can solve the differential equation. It's a separable differential equation. I have to integrate both sides. Now this integral should look a little similar. We just did one earlier. So what we can do is use partial fractions to solve that integral. So if I do that, this equation pops out. And from that, I get two equations. I get this equation for A, and I get this equation for A and B. And so if you solve for A has to be 1 over 200, and that means B has to be equal to A, which is 1 over 200. So I can plug them back into my partial fractions representation and solve these integrals. Now, we get this expression. I can multiply by 200. I can use properties of logarithms to write this. Now I can take the exponentials of both sides. I can use properties of exponents on this to write out a new constant, which I'm calling P0. I apologize for my equations here. And then I can solve for P. And I didn't go through all the algebra for solving for P, but I've done that earlier. You guys can go through the algebra if you'd like. And then I find P. So my initial condition says the population at t equals 0 is 100 million. And so now I can solve for P0. If you solve for P0, you find out that P0 is 1. That makes our population model equal to this. And now I got to find out what happens in the year 2020. Well, in the year 2020, that's 60 years from my t equals 0 time. So I plug this in, plug 60 in for time, and I get the population should be 153.7 million people. Alright, so here's another population model, or problem. So they claim, what they're telling you is we have some data of population right here, and that this fits the population, this fits the logistic equation right here. The problem is we do not know M and K, and I need to find M and K. What I'm going to do is approximate the derivative by using the slope between two successive points. So let's say for 2000, But for 1925, I know the population in 1924 and 1926. So I can calculate the derivative. Okay, so our initial condition is 1925, so I'm going to say t equals 0 at 1925. And we have a population of 25 million. So I'm going to plug that into my differential equation right here. I'm going to approximate the derivative by taking the population in 1926 and subtracting it from 1924 and dividing it by 2 years. I know the population at that time is 25 for 1925. And so that gives me an equation in terms of K and M. But it's one equation and two unknowns, so I need another equation. The problem suggests we use the data for 1975. So I take the population of 1976 and subtract it from the population of 1974, divide it by 2. I know the population of 1975 is here. So the idea is I'm calculating the slope or the derivative for year 1975 by using this approximation, and that gives me another equation for M and K. So I have two equations now and two unknowns. If I solve them, I get this value of K and this value of M. And so I can use that and plug them back into my differential equation, but I have to solve my differential equation. And so this looks, it's looking kind of familiar. It should be looking kind of familiar. So I have to solve this integral using partial fractions. If I do that, this expression shows up, which gives me these two equations. So A has to be 1 over M, and B has to be equal 1 over M. And then I can solve my, represent this integral in terms of my partial fraction representation. And then I can solve these integrals, multiply by M. I've left out all the mathematics or algebra between there. I figure you guys can do that. We've done it several times already. Now I need to solve for P. That's when I solve for P. I need to plug in what M and K. I should say you can plug in what M and K are and actually solve for the population at that point. And I'm going to leave that up to you guys to do that. I'm going to move on to the application problem. So there's an application problem that gives you data or has you find data from a chart that's in a book, and you get times and year spaces and populations at that time. So how do we solve that? Well, they give you this population model right here, and it's technically a logistic population model where K in this thing is equal to 1, but I'm going to rearrange it in a little different manner this way, because the reason I'm doing that, if you see this side, the right hand side of the equation is now a straight line for population. So what we're going to do is use our data to approximate the slope of the line for this point right here by using a point behind it and a point in front of it. So let's say we can approximate the slope for the year T2, because I have population for P2 and P3 and P1. And so the idea is this is an equation for a straight line. So I'm going to write it this way, where our Y value is 1 over the population for a particular time period divided by the derivative. Our y-intercept value is our constant A, and our slope is our constant B, and our x becomes P. But the idea is I got to create a series of points where I can plot these points and create a straight line. And the way I'm going to do that is I'm going to approximate the derivative at a particular time, say T2, by using the data for the population for the year after it and the year before it, and so I calculate it this way. Then I actually have, here's my differential equation, so I actually know an approximation for my derivative. I know what the population is at that point for T2, it's P2, and I can plug that in there, and I can get a series of these points. Well, why do I need a series of these points? Well, I don't know what A and B is from my population model up here. I want to get A and B. Well, this is a straight line where this is your Y, and this is your P is your X. So I take my X points and my Y points, and I plot them on a graph. I fit a line to that graph, and my slope is my constant B, my y-intercept is my constant A, and now I have A and B to use my population model. That's what the applications problem is going to have you do, and you're going to have to either do this in a spreadsheet and have you fit the line, or I'm going to show you in class how to do this in Maple and have Maple fit the line for you. So I'll see you in class.